If we have a string that's attached at both ends, much like the demonstration that we did a few days ago, and we send a wave down at a particular frequency, the wave reflects back at the same frequency, for the most part, we will see an interference pattern that looks random. It's not random, but it looks random. If we increase the frequency, it looks like a different random interference pattern. If we increase the frequency, all of a sudden, something unique happens. We see what we call a standing wave. It makes it look like the wave is standing still. This is the first one that we would see. We call this the first harmonic. The first harmonic consists of one, what do we call this bump here, this constructive interference? We don't really call it a crest in this context. You could. It's not wrong to call it a crest, but specifically we call it an antinode. Remember that term? Antinode, and then we have a node at both ends. If we increase the frequency even more, then we see a standing wave that looks like this. And if we increase it even more still, eventually we see a standing wave that looks like this. Most of the frequencies produce not random, but it appears to be a random interference pattern, but special frequencies that we call, what's that R word? Resonant frequencies produce standing waves that make it look like they're standing still. All right, the length of this wave is L, or sorry, the length of the string, I should say, is L. We're going to say L is how much of a wave here? This is a half of a wave. Now, therefore, lambda is equal to 2 times L. We're going to say V is equal to F times lambda. F is equal to V over L, or V over lambda, I should say. Or we're going to say F is equal to V over 2 times L. There's the frequency, we say, of the first harmonic. Now, we could derive an equation for the second harmonic. We did that on Friday of last week, but we don't need to because we know the second harmonic is just twice the first harmonic. So if you calculate the first harmonic to be V over 2L, the second harmonic would be twice that value. And the third harmonic would be 3 times that value. We can always, if we want, derive an equation for the third harmonic. But in my opinion, as long as you can find the one for the first harmonic, why would you bother finding the equation for the third harmonic? Just multiply the first one by 3. All right. Remember the rule that we said on Friday, if you're going to do this, okay, if you're going to do it this way rather than derive all 3 equations. If you've got a question where you have the first harmonic, great. If you have a question where you don't have the first harmonic, then get it. No matter what you're looking for, get the first harmonic. You're always going through the first harmonic. If you get the third harmonic, divide by 3 to get the first. Okay, if you get the 17th, divide by 17 to get the first. If you have it, great, work with it. If you don't have it, get it, and then work with it. You're always going to do something with that first harmonic. Now, we had some questions on a worksheet that were due for today, 11 of them. I gave you some answers a few minutes ago. Which question or questions would you like to go over here? We'll pick 2 or 3 of these to go over before we move on to our next thing here. All right, 5 and 11 it is. 5 says the length of a particular vibrating spring is 1 meter. The speed of wave is 1,000 meters per second. Oh, what's the wavelength of the first harmonic and the frequencies of the first 3 harmonics? Okay, interesting. Let's draw this out. That's what we do. We draw it out, we derive an equation for the first harmonic. Remember, there's no point in deriving an equation for the third harmonic. We can always go through the first. So here's the first harmonic. For this one, we say that L is equal to 1/4 lambda, or lambda is equal to 4 times L. If we want to find the wavelength of the first harmonic, why don't we just say lambda is equal to 4 times 1.00 meters. There we go. There's the wavelength of the first harmonic. Yeah? I don't know. Why is it 4? Should be 2, shouldn't it? Yeah, it should be 2. 4? Well, Patrick, thank you for passing the test. I mean, Parker. It's been a while since I've done that. I just called you Patrick. Parker, thank you for passing the test. Parker, the wavelength should be 2L, right? It's exactly what I meant to write down. I just wrote down 4 just to see if you guys are paying attention, right? So instead of being 2L here, it's going to be 4L. I mean, instead of being 4, it's going to be 2. I told you I was tired. which gives us a wavelength of 2.00 meters. Thank you, Parker. Now, we want to find the frequency of the first three harmonics. Let's go from here over to here now. Frequency is V over lambda. F1 is V over 2L. So let's find that. V is, what is it, 1,000 meters per second? Divided by 2 times the length of 1.00 meters. Gives me, I think, 500. Okay, there's F1. How do you find F2? Well, you could derive the equation for the second harmonic. Or you could just multiply this one by 2. So the second harmonic would be 1,000 hertz. And the third one would be 1,500 hertz. Remember, we've got something about the first harmonic there. That's great. Solve for the first harmonic. And then if you're looking for the third, then multiply it by 3 to get the third harmonic. Always use the first harmonic to do what you need to do. And the last one is number 11. Number 11 says, how long of a string is required to produce a first harmonic if the speed of the wave in the string is 600 meters per second and the frequency of the third harmonic is 780? There's a red flag right there. There's a red flag right there. Third harmonic is 780 hertz. We don't care what the third harmonic is, do we? We care what the first harmonic is. So let's get the first harmonic. What is the first harmonic here? What is it? 780 divided by 3. So it's 260 hertz. Now, we also have a speed of 600 meters per second. And we're looking for the length of the string here. So let's draw this out. First harmonic. We're going to say L is equal to 1/2 of a wavelength. Lambda is equal to 2 times L, Parker, right? Lambda is equal to 2L, is that right? So we're going to say F is equal to V over lambda. F is equal to V over 2L. Let's solve for that frequency now. V is 600 divided by 2 times, we're looking for length, right? So let's say F is equal to V over 2L, and now let's rearrange that to solve for L. L goes up, F goes down, V over 2F. So this time it's 600 divided by 2 times 260. That gives me a length of 1.15 meters. Is that okay? If we have an air column, and an air column would be like a water bottle, right, with water in it, with Coke in it, whatever. You blow across the top of it. It's like most wind instruments that you blow across. It's open at one end, it's closed at the other end where your mouth is. Okay, we get interference of sound waves taking place, just like we have interference of waves in a string taking place. This interference pattern of sound waves can, just like with a string, produce standing waves. But the standing wave will look a little bit different. The first harmonic is going to look like this. We have to, if we have an open end and a closed end, we have to have a node at the closed end. We must have a node at the closed end and an antinode at the open end. That's the first harmonic. The next one that would be produced would look like this. Remember we had in the first one, Friday, when we were looking at 2 fixed ends, a string attached at both ends. We had one antinode in the middle. Here we have one antinode in the middle. Then we have 2 antinodes in the middle. And then we have 3 antinodes, and so on and so on and so on. Tell me, how much of a wave is this length? How long is this string relative to the length of a wave? Let's draw that out over here like we did on Friday. Okay, we're going from, where are we going from? From here to here. How much of a wave is that? Yeah, it's a quarter. So we're going to say that L is equal to 1/4 lambda, or lambda is equal to 4 times L. Just like what we did on Friday, except on Friday it was 2L. Today it's 4L. Let's look at the next one. We're going from here to here. How much of a wave is that? Who said that? Good. 3/4 of a wave. Good. So we're going to say L is equal to 3/4 lambda. And lambda is therefore equal to, if we rearrange this, the 4 goes up, the 3 goes down, becomes 4/3 L. Next one. We're going right to here. How much of a wave is that? This is a full wave, right? This is another quarter on top of that. 1 1/4. 1 1/4. We're gonna write it as an improper fraction, though, just so you can see the pattern formed in a minute here. So we did exactly the same thing we did on Friday when we had a string that was fixed at both ends, but this time the equations are a little bit different. The idea is the same, the equations are a little bit different because we have to have a node at the fixed end, the closed end, and we have to have an antinode at the open end. All right, let's derive the equations a little bit further now. Let's say for each of those, V is equal to F times lambda, or F is equal to V over lambda. Let's replace lambda with, in this case, 4L. That's the frequency of the first harmonic. Remember the frequency of the first harmonic for the last one? What was it? V over 2L. This time it's V over 4L. Let's look at this one. F is equal to V over lambda. Oh, what's lambda? 4/3 L. Well, that's not a very nice looking equation. So let's simplify that a little bit. Divide by 4/3, same as multiply by 3/4, becomes F is equal to 3V over 4L. And then the next one, F is equal to V over 4/5 L. Let's simplify that. F is equal to 5V over 4L. So the equations are different, but it's the same basic analysis. But I want you to notice the pattern here. On Friday, when we had a string that was attached at both ends, we had the first harmonic, and then this next one was twice the value of the first harmonic. How do these ones compare? V over 4L, 3V over 4L. This is what? 3 times. We're not going to call this the second harmonic. We're going to call this the third harmonic. What about this one? V over 4L, 5V over 4L. That's 5 times. We're going to call this the fifth harmonic. In other words, what we're saying for these ones is that there is no even-numbered harmonics. They don't exist. When I blow across the top of the water bottle here, okay, you're hearing the first harmonic, maybe the third harmonic mixed up with that, but you're not hearing the second harmonic. They don't exist. They can't physically exist because you have to have an antinode at the open end. Now, just like with the strings that were attached at both ends, we're always going to go through the first harmonic. So the reality is, if you remember this, you're good. As long as you remember along with this, that the next harmonic would be 3 times the first, not twice the first. And the next one after that would be 5 times the first, not 3 times the first. Okay, does that make sense? So exactly the same thing, except different equation and no 2, 4, 6, 8, 10 numbered harmonics. Now, this is pretty typical, let's say, wind instrument or brass instrument. Right? You blow across the top of something that's a closed end, the other end is open, and the first harmonic would be whatever the speed is divided by 4 times the length of that instrument. The third harmonic, the second overtone we'd call it, would be 3V over 4L, 3 times the first frequency, and so on. If you have an instrument where we have 2 open ends, or if you just have a pipe, like just a regular PVC pipe or a regular steel pipe, and you blow across the end of it, you're going to hear a sound. It's going to be a different sound than you hear in this water bottle because the resonant frequency is different. Let's draw these ones out. Here we have, remember we said we have to have an antinode at the open end? The first harmonic would look like this, where we have 2 antinodes and a node in the middle. Next one would look like this. 3 antinodes. Next one would look like this. Oops, messed up on that. Where we have 4 antinodes. The length of this one is a half of a wave. Lambda is therefore equal to 2L. The length of this one is one wave, which is L. The length of this one is, this would be 1.5 waves. Or L would be equal to, lambda I should say, would be equal to 2/3. F is equal to V over lambda. F is equal to V over 2L. Hey, you recognize that equation? Parker, recognize that one? Same as the string, right? When you had a string that was attached at both ends, the first harmonic was V over 2L. When you have an air column, like a pipe, a simple pipe that you blow across the end of, the first harmonic is V over 2L. Now, you'd hear a different sound because the speed of sound through air is different than the speed through steel wire or string or whatever, right? But it's the same mathematical expression to describe that harmonic. Now let's take a look at this one. F is equal to V over lambda. This one would be V over, F is equal to V over, what would it be? Just L. And this one is, what, V over lambda? Or V, F is equal to V over 2/3 L? Which is the same thing as saying F is equal to 3V over 2L. Notice the pattern here. We call this the first harmonic. The second one here, V over 2L, V over L. This is twice the value of the first one. This one's 3 times the value of the first one. So we're back to having all the harmonics. Remember Friday when you had a string, first, second, third, fourth, fifth. Now when we have an air column that we say is open at both ends, first, second, third, fourth, fifth. When you have a closed air column, like blowing across the top of a water bottle or blowing across the top of a clarinet, let's say, then we would say that we have a closed air column where there is only the odd harmonics, F1, F3, F5, not the second, fourth, and so on. Once again, you're good with going through the first harmonic. Remember, though, when you have second harmonic, fourth harmonic, the odd harmonics, and when you don't. The rule of thumb is this. If both ends are the same, it's a string that's attached at both ends. It's a pipe that's open at both ends. If both ends are the same, you got all of them. F is equal to V over 2L, twice that, 3 times that, 4 times that. If you have two ends that are different, like a clarinet, where you have one end open and one end closed, then your first harmonic is V over 4L, not V over 2L, and you don't have a second, but you do have a third. You don't have a fourth, you do have a fifth. Now there's one more thing that I want to show you here just before I do a couple of questions here. Because we're now dealing with air columns, right, blown across the top of a water bottle, blown across the top of a flute or of a clarinet, blown across the end of a pipe, PVC pipe or steel pipe or whatever, we're dealing with sound waves in air. So there's one more equation I'm going to give you that will provide for you the speed of sound in air. It looks like this, 331 meters per second plus 0.6 times t. We talked about this very, very briefly on Friday, but today we're going to actually use it. The speed of sound only in air, this doesn't work for strings or steel or water or anything else. The speed of sound in air at standard pressure, standard atmospheric pressure, is 331 meters per second plus 0.6 times T. What does T stand for? The temperature in degrees Celsius. So if you have a temperature that is 10 degrees Celsius, what's the speed of sound? We would say 331 plus 0.6 times 10, which is 331 plus 6, which is 337 meters per second. Find that as the temperature goes up, the speed of sound goes up as well. All right, let's do the first example problem here with this. This one's not in your book either, so I'm going to ask you to copy this one out just like last time. says, what's the frequencies of the first two harmonics observed in a 40 centimeter long closed air column if the temperature of the air is 30 degrees Celsius? A couple of things we got to spot here. Firstly, that we got centimeters and we want meters. We don't want that. It's a closed air column. A closed air column is an air column that is open at one end and closed at the other. It's like the water bottle. Okay, and when I blow across the top of a water bottle, this is a closed air column. Open at one end, closed at one end. We also have a temperature here. What do you think we're going to do with this temperature? Let's find the speed of sound. 331 plus 0.6 times the temperature. So 331 plus 0.6 times 30. 0.6 times 30, I believe, is 18. 18 plus 331 is 349. So here's the speed of sound in air at 30 degrees Celsius. Yep. No, that's Facebook column. Yeah. Yeah. Now, let's draw out the first harmonic. We're looking for the frequencies of the first two harmonics, but we don't really need to do anything with the second harmonic other than multiply the first harmonic by something. So let's draw the first harmonic. Remember, the first harmonic in a closed air column has a node at the closed end, okay, a node down here in the water bottle where the water is, and an antinode at the other end where it's open. We're going to say L is equal to 1/4 of a wave, or lambda is equal to 4 times L. We're going to say F is equal to V over lambda, or F is equal to V over 4 times L. Now, when I solve for that frequency, that's going to be the frequency of the first harmonic. We say it's 349 meters per second divided by 4 times the length of this, which is 0.40 meters. Let's do this one together. Remember what our rule of thumb usually is when we're doing problems like this with a calculation on the bottom? Do that one first. 4 times 0.4 gives me a value of 1.6. 349 divided by that gives me a value of 218.125. Why did I write down that unrounded number, 218.125? Because what? I got to find another harmonic, so I'm going to use that number. And I want to use the unrounded number. Now, what is the next harmonic? What do I multiply this by? 2 or 3 or 4 or 5? By 3. The next harmonic, the first two harmonics is the first harmonic and the third harmonic. There is no second harmonic. Remember, if both ends are the same, all of them. If both ends are different, like we have here, then only the odds, no evens. So we're going to say 3 times 218.125 gives me a value of 654. There we go. So we first had to get the speed of sound in air because we weren't given that value. Given the temperature, though, it's almost as good. Then we found the frequency of the first harmonic, which was V over 4L, because it's a closed air column, not V over 2L. And then we multiplied it by 3. It's pretty much like the questions you did on Friday, right? Except that you have to find the speed sometimes of these questions. And there is no second. To find the next harmonic, you're going to multiply it by 3, not by 2. Good? One more example here. Oops. No, it's not there. Rather than that example, I'm going to have you work on the back side of the worksheet that I gave you on Friday. There's 11 questions. Now, pay attention to the question. Some of these are open air columns where both ends are open. Some of these are closed air columns where one end is open and one end is closed. The analysis of them is almost identical, but remember that if you have an open air column, V over 2L, and then you have 2, 3, 4, 5. If it's a closed air column, it's V over 4L, and it's 1, 3, 5, no 2, 4, 6s. And also remember that that speed of sound in air is 331 meters per second plus 0.6 times t. All right, take a look at that second side of that worksheet here now. I'll give you some time to work on those, and then we'll go over one or two of them, and then we'll give you some more time to work on them. Okay, let's have a look up here at number 4. It says the temperature of the air inside a particular closed air column is 18 degrees Celsius. The air column is this long. What's the frequency of the first harmonic? There's my closed air column. There's my first harmonic. And we know that L is equal to 1/4 lambda, or lambda is equal to 4L. F is equal to V over lambda, or F is equal to V over 4L. That's good. Now we have an equation, but we do need the speed here. The speed here is 331 plus 0.6 times 18. That gives us a speed here for number 4 of, I don't know the value of that. I don't have that. 341.8, is that right? 341.8 meters per second. So now we're going to take that value. We're going to plug it into this, 341.8 meters per second, divided by 4 times the length of this air column, which is 0.5. Say 341.8 divided by 2, basically is what that amounts to, ends up being 171 hertz. Now, we were asked for the first harmonic in question number 4. But if we were asked for the second harmonic, we would have just doubled that. Third harmonic, we would have just tripled it. When we're using V over 2L, because we're using a string that's fixed at both ends, or we're using an air column that's open at both ends, there is first, second, third, fourth, fifth harmonic. When we're dealing with V over 4L, oh, wait a second here. This is a closed air column. It's closed air column, V over 2L, we have first, second, third, fourth, right? If we have V over 4L, a closed air column, then the first harmonic would be 171. The next one that we would hear would not be the second harmonic, rather it would be the third harmonic, so we'd multiply that by 3. We're not looking for the next one, but if we were, we would simply take F3, multiply 3 times the value of F1, and then we could say F5 is equal to 5 times the value of F1. There would be no second or fourth harmonics because it's a closed air column. If it's open, second, third, fourth. If it's closed, third, fifth, seventh. Now, number 9, somebody asked me about number 9 as well. It says the frequency of the seventh harmonic of an air column is 770. What's the frequency of the first 4 harmonics heard? Well, remember what we said. We always go through the first. If this is F7, then F1 is going to be F7 divided by 7. So 770 divided by 7, F1 is going to be 110 hertz. So far, so good? Okay, what's the next one that's perceived? The next one that's heard? F1 is 110. The next one is going to be F3, which is 330. The next one is going to be F5, which is 5 times F1, which is 550. The next one is going to be F7, which we already established is 770. And the next one is F9. It's 9 times F1, or 990 hertz. So sometimes we need to use that derived equation, F is equal to V over 2L or V over 4L. Sometimes we don't. Sometimes we just need to take the frequency we have, divide it by a certain value to get the first frequency, the first harmonic, and then multiply it by something else. Okay, who asked me about number 9? Cameron, was that you? Does that make sense? Okay. Don't make them harder than they have to be, right? If you have a seventh harmonic, great, get a first. Like, whatever you do, get a first harmonic. Okay, I don't care what you're looking for, get the first harmonic. If you have to use V over 2L to get the first harmonic, do it. If you have to use V over 4L, do it. If you've got 770 as a seventh harmonic, then divide it by 7. Do it. Whatever you do, get the first harmonic. Whatever way seems appropriate to do that. Let's also take a look at question number 11, the last one we'll do here today. Right, Rachel? Number 11 says, the length of a particular closed air column, it's a good idea to identify that so that you know which equation to use, is 60 centimeters. The frequency of the third harmonic is 432. What's the speed of the sound in the air column? What's the rule? Go through the first. Get the first. Here's the first harmonic. Here's the first harmonic. We know that L is equal to 1/4 lambda. Lambda is 4L. F is equal to V over lambda, or F is equal to V over 4 times L. There's my equation. Good. We want to find the speed of the sound. So let's rearrange that. Let's get V is equal to 4 times F times L. Good. 4 we know. F, oh, what's F? 432? No. What's F? That's the frequency of the third harmonic heard. We have the first, we have the third, we have the fifth. 432 divided by what? Right. And 432 divided by 5 is 86.4 hertz. So the third frequency heard here is 86.4 hertz. Now we're going to multiply that by 4, and then by the length of the air column. Do that, works out to be 207 meters per second. Right? Always go through the first. We've got a fifth harmonic of 432. Then get the first. Whether you use V over 2L, V over 4L, or whether we just divide it by 5, get the first harmonic. And then do your work with the equation for the first harmonic. It's not the only way to do it, but it is, I think, the easiest way to do it. Question, Rachel? No, it's the third harmonic heard. And the third harmonic heard in a closed air column is the fifth harmonic. Remember, in the open air column, we have 1, 2, 3, 4, 5, and so on. So the third harmonic heard would be the third. But in a closed air column, 1, 3, 5, and so on, the third harmonic heard would be the fifth. Does that make sense? Rachel, does that make sense?